Okay, thank you everybody. Thank you, Ramon, and the organizer for giving me an opportunity to present my work. My background is in computer and engineering, but I try to not talk about engineering equation, but present a clearer picture of the current state of quantum computing that we have. And we are just looking for additional application. And at this point, I will talk a little bit about the concept of quantum computer, and then we'll go specifically into the area that I'm working on, quantum memory, and we will walk you through the idea of how it's being used in a computer right now, and how me, with the background in engineering where I work a lot in the area of artificial intelligence, how I collaborated with Ramon and psychology researcher so that we can mimic what is being done in the human mind with computer. And after that, we will show you how we are doing some of the work right now with the quantum memory. And I'm proposing a two-way collaboration so that people in psychology can help us understand more about the human thinking process so that we can mimic it with faster computer to make our computer more intelligent, but at the same time, we can provide the researcher outside the area of computer science area so that they can take advantage of what we are achieving from the computer science perspective. So if we do a quick search about quantum computer, it will show up that a few years ago, Google announced that they have a very fast quantum computer, the first working model. And from Google perspective, they want to show everybody that they have a very fast computer. So in the search with the link that I provided here, this is the picture of the quantum computer that Google built. And they claim that it's running very fast in terms of 1.5 trillion times faster than the fastest traditional computer that we have. And to put that in another perspective, when Google said that if we have something that requires a supercomputer that we have today to run 10,000 years, their computer only requires 200 seconds to finish. And for us working in national security, we work about the encryption technology where we protect data, and most of the encryption algorithm that we have is they are developed to be breakable, but it's not computationally feasible to break an algorithm for encryption because it requires so much time to break it in terms of 10,000 years, 20,000 years. But now with the new Google quantum computer, we can see immediately that if they have this computing machine, they can break it anytime they want. So with the quantum computer that we have new question that at least in my mind, and we ask ourselves, now that we have a fast computer, what do we do with those computer if we have our hands on them? And that is the idea that I'm working on right now, one of the ideas. And the idea is that can we take advantage of the new capability to introduce new application. And right now, Google is still in the early stage of developing a quantum computer. So there's no standard how to design the hardware or software. So what they do is they design everything in parallel with our current computer design so that they can benchmark or compare the performance. And at this point, the performance is so extremely good that it asks our introduce those two questions. Can we use them in some capacity? So in for us in engineering, we design machine typically based on the needs. For example, I don't want to take out the trash every morning, so we work on robotics so that they can do the job that we don't want to do. And we also show from a lot of research that we have to do calculation, and we don't want to do detailed calculation. We want to focus on the area of research that we work on. So we invented computer. Well, first we invented calculator, and then we move on to computer that has better capacity. And now we introduce another layer of more advanced computer with Google quantum computer. But the idea is that if we use those new capacity, most of us would try to think about using it in terms of what we need, and we normally try to mimic how we get things and then implement the solution on the computer to do it. So for computer, we mimic the human mind. We wanted the computer to be able to do processing of information. So we have some basic understanding of the human mind where we will have to have some sort of memory storage to keep the information before we do the processing. And we have to do the processing unit, and we have to do some kind of interface so that we can interact with human. So that is just the basic mimicking of the human, how we do things in our mind and how we communicate with other people. And for the computer software side, we do those things. We want to make it more flexible by doing instruction so that the computer hardware can do processing and follow the instruction that we program it to do. But for us in computer area, when we do provide the memory, we keep the data there on a permanent basis, and we will be using those data in the future when we need them. So it's very similar to the way we put information in our memory, and we figure out how, when, and how we need those information. So for us in computer science, we when we provide memory, we have to provide based on this space capacity, how much memory, how much information we can put into the memory. And we also need some procedure how we put in the data in the storage and how we retrieve them. At this point, we begin to be different from how the human mind works. We can provide those two functions that are similar to the function of our human mind, but the way we implement those two functions will be different. So here, the function that we have are implemented differently, and I want to demonstrate some idea about how we put it into the computer hardware. So what we did was we built some hardware that provide a memory bank, and the memory bank is just a set of bits and bytes that can hold data that we put in. So anytime we have data, we say we want to save to the memory. So we put the data there and it's electronically saved to the hardware and it will stay there on a what we call permanent basis. I know that from the human point of view, permanent is a little bit strong, but it's as long as we have the hardware, we can provide the data. So next time we have new data, we put it in the memory bank. So we search for the block where in the memory bank where we don't have data and we put the data there and that will occupy another block. And we keep on doing that. Anytime we have data, we will put it there. But with computer hardware, eventually we will occupy every single bit of the memory that, that memory bank that we are providing. And this is the problem with us in computer science. Whenever we use up the memory bank, the problem is if we keep on putting new memory into the memory bank, either we override the existing memory that we put in, or we interfere with the reserved memory area where we allocated for the operating system to use. And this is the common problem that we had whenever we interfere with the operating system. This operating system will crash. And this is a very common event with Microsoft software. It's less frequent now, but it can still happen even now in 2021. So when we work with the the quantum computer is super fast as Google advertised. And I just want to talk a little bit, not so much about the technology, but the quantum computer was developed around the idea that we are using the quantum bit as opposed to our traditional computer that are designed based on the binary bit. So with the binary bit, the memory unit can hold the value, electronic value between 0 and 1, and we represent those two binary values on the electronic voltage that we use between 0 and 5 volt. For the quantum bit, it can be any value between 0 and 5 volt. And the idea is that with the traditional computer, the information have to go either 0 and 1, and the electronic hardware require us to wait for when we change the value from 0 to 1. There is some time that require the electronic to perform that changing. And after the changing, the sensor will require the value to hold at some time so the sensor can recognize the voltage. And that introduced what we call a computing cycle. In the old day, we require something like a cycle is a computer can perform like 1,000 to 10,000 cycle per second. Now our computer can perform between 1 billion to 1 trillion cycle, depending on how much we spend on the hardware. But nevertheless, the cycle is still there, and that restricts our capability of computing. With the quantum computer, we are changing continuously, and we design the sensor to recognize the voltage instantly. And that is why it's performing so fast comparing to the traditional computer. But with the quantum computer, they still require some memory so that we can hold some temporary result in the computing. that they are doing. Just imagine we are asked to do a simple calculation of 2 times 3 plus 1. So in our mind, we have to multiply 2 times 3, and the intermediate result is 6. And we have that intermediate result so that we can go to the next computing cycle to add 6 plus 1 to get the final result. So with computer, we have to have that memory to hold the intermediate result, and we do that with the analog memory that will hold the quantum bit. So it's from us, we provide that to the CPU of the quantum computer, but we don't see any additional advantage of providing analog memory. We can easily use the traditional memory to mimic and provide some simulation. But my point is that at the beginning, I asked ourselves, what do we do with that quantum computer? And if we are going with the current design to design everything in parallel with the traditional computer to benchmark, then eventually our analog memory bank will run out the same way that Microsoft software had problem with the traditional hardware. So what we want to do is that we want to learn from people in psychology about the human mind, how we work with memory so that we can design a better computer to improve the storage capacity. So for us, on the casual observation of the human mind, it seems like that we don't have we don't have any problem with holding data. We don't have to erase the data. It's always there in some manner. It might seem fading, but it's still there. And if we spend effort, we can record the data for use. So here is what I want to demonstrate from the visual point of view. Here, if we have an image, we see that with our eyes and we put it in our memory. This is not 100% visualization of the memory. It's just to illustrate the point of how we work. So as time passes, the memory seems to be fading away like this, but it's still there in our human mind, and the information is still there for us. It just requires we learn how to record the information to use it again. Another observation is that our capacity seems to be having no limit. So here is what we have with memory. Same procedure, we put what we see into our mind and we register that as memory. But the next time we see something different, if we go through the same process and we put it into our human mind, it seems like they are mixed together in some manner. And that is something that we want to do with the computer so that we don't have to run out of storage capacity. And that is the research work that I'm working on. And what we do is that can we imitate that unlimited capability so that we can implement that with a quantum computer or actually with a traditional computer as well. So here, going back to what we want to do with the data, we save it to a block in a traditional computer. We do the same thing with the quantum computer. The difference is this: if we have new data, with traditional computer, we have to save it to a block that is not occupied. But what we want to do is we want to save it over the existing memory in the quantum computer. We are still restricted to the number of cells in the quantum memory bank. But if we do it like this, we can improve the capacity more. So just imagine I can put many images into the memory bank of the quantum computer. We improve the capacity of the quantum computer more. So in our order to do that, we devise an algorithm to do the overlapping of data into the memory. And it turns out that it's extremely easy to do. It's just a mathematical calculation. But what we want to do now is when we put data there, how we record the data back when we need the data. And that is something we want to learn from the human mind. We don't understand the process, but I cannot wait for Ramon or anybody from psychology to do that because they're waiting for me to provide the computer, faster computer for them to understand. So it's a circular situation. And what we begin at this point, if we try to apply some of the computational technique that can help us to do that, to demonstrate the capability, and at the same time use that capability to help researcher in psychology so that they can help us to push the technology further. So the first step is that we, from artificial intelligence, we observe ants and we develop some algorithm that we call ant colony optimization problem. And I'm applying that technique into how we save data to the memory. And I push it a little bit further so that we can record the data. And the idea is that each time we put data into the memory, we mark it with some information, just like the ant, they mark their path with some chemical that they produce that we call a pheromone. So we mark the information we put into the memory with some identification that we call that the amount of pheromone that we mark. And each time we put in new information, the old pheromone will evaporate, just like in real life with ants, so that each piece of information is marked with a unique amount of pheromone. So whenever we need to record them, we check the pheromone identification and we can record the information back based on that unique identification, and we mark each piece of data we put in. And in this way, we can stack different data, and I'm working with images so that we can visualize the process. But in reality, any type of data can be done in the same manner. So in the ant colony optimization, what we observe is that ants is just wandering around to look for food, and whatever the path that they went through, they mark that with the chemical scent that they produce, and that will help them to navigate back to where they came from. So once the first ant is reaching the food, he will bring the food back and he follow the path that has his pheromone. The other ants eventually will be able to reach the area of food, but what they do is that they follow the path with the strongest pheromone, and that allows them to ignore the longer path, and they go very efficient with the shortest path to their ant hill. And that's what we observe, and that's what we implemented to solve the optimization problem. So what we do in this memory model is that each time we save the data to the memory, we are always using the same memory block. And each time we save it, we mark it with some identification number that represent the amount of pheromone. And we always begin with the maximum allowable. And each time we allow the new memory to come in, the existing memory will be reduced in terms of the pheromone that we mark. And this is the important point with traditional ant colony optimization. We just arbitrarily reduce the amount of pheromone. But with this specific application, we have to figure out the function that represent the evaporation in the manner that we can do everything in one overlapping memory, but in the manner that each piece of memory will be still unique with the amount of pheromone that we mark. So that is the important thing that we get in this research. So the new GAGA will be combined with the old GAGA, but we don't have to repeat with every single piece of image. We just take whatever is in the existing memory, which is already a combination of many images. And we just do a simple mathematical calculation and we can mix them together. So here is the interesting point we showed so far was easy. This is the most difficult thing we have to record the data. And in this application, we don't know the data. We just have some sort of description of the data. And we have to solve a big linear equation to extract additional information so that we can identify the data associated with the identification of the pheromone that we mark. So that we can talk more later on because that is the restriction of this research right now about how much we can put into the data storage, but it's almost unlimited. So with the implementation, I don't have my hands on the real Google quantum computer. So I do it everything on simulation with my own computer. So we work with data in terms of images so that we can visualize how it's done. But as I mentioned before, you can apply any type of data that you want to use. So in this first step, I use images and it has two characteristics. One is a color and one is a shape. And the idea is that we want to mimic the human mind, how we recall information, not based on 100% of the description, but on partial description of the information that we retrieve. So here we do the same thing. So the first thing is that if we want to record something, we say that I remember I put something in the memory that has a color blue, but I don't remember the shape. So that is what I'm working on right now. So the memory will collect the data and we have the processing layer that will try to look into what is blue and retrieve out as this original image. So with the procedure I just put in, we can mix in different images and they're fading with time. And we do that on the traditional computer, mainly because I don't have a quantum computer to work with and I don't want to wait. So here is what we put into the traditional computer. We have to convert that to our traditional convention where we convert data into quantum bit. But at the next level, we put it into traditional memory here where each quantum bit will be represented by a number of bytes that we have in the binary computer. So this is how I put the implementation. But the software that I do there is an open source with Java, so everybody can request and play with it. And after we solve the important linear equation that I mentioned, we ran through experiment and we began playing with different shape and different color. We can mix them together into a single image that represent a single block of quantum memory. And the next step is we want to retrieve some data from that. So I begin to retrieve, instruct the program to retrieve something with just the color red. I don't know what shape that has the color red in the computer. And with us, our human eyes, we can see something with the color red and we can guess the remaining, but with the computer, they only see numbers. So that is the challenge for us working in computer. So we analyze each pixel of the image that represent the memory. So we analyze them, we get the reverse calculation. We can see that this, on the first result, we can see this containing the number of pixel that represent the pure color. And then on the second image, we include pixel that are mixture of two color. And on the third one, we recover pixels that are the result of overlapping many colors. So we were able to recover every bit and we were able to reconstruct the shape that we put in the original color in. So that is our current status right now. We began changing the shape a little bit to make it more interesting, make it more relatable, and we can still do the same thing and with no problem at all. So the next step is for us to increase the complexity of the data instead of just one single color. We want to mix many color into the image, and that will make the computational procedure more complex. But hopefully with the quantum computer, we can do that fast. So here is where we want to talk to Ramon. We want to talk to researcher in psychology. So Ramon told me that a little bit about the memory. So the hypothesis is that when we look at our computer, look at our mind, if we see something, we put it in the memory, but at some point that memory will begin to fade. But if we reinforce our memory with the same thing, then it will be stronger. So it's similar to me when I was in elementary school. I have to memorize a lesson. I repeat that lesson many times so that I can put it in my memory. I didn't understand how it happened. It just happened and I get that to put data to my memory. So this is what happened. And we were able to simulate that with computer and allow us to see the simulation where each time we put in a pattern, it will reinforce what is in the memory. And with that, we ask ourselves, what is the next step? And from the engineering point of view, I immediately think of a pattern that we use for computer with dot matrix printer. So with the pattern of circle that we simulated earlier, I asked myself if we can simulate a pattern to represent characters, can we do some psychological test? And one of the things that I remember I read somewhere was about the use of the word that can help us in the memory. and the association of what we read and what it represents. So one of the experiments that people did earlier was that when they talk about color, if they use it with the corresponding color with the word meaning, then they can improve memory like this. When they talk about red color, we use the color red to highlight the text, and the reader can remember it easier and faster. So they went through the experiment showing that, and they asked the people that they are testing with, what was the first word that you saw, and normally people can associate that with the actual color that we show, and it's easier to recall from memory. And the experiment also mentioned that if we mess up with different color, we mess up with our thinking process, we make it more difficult to remember. So when you see something that reflect the meaning that is green color, but you see that with a different color, our human mind will be busy because we are confused, and it's much will be much more difficult to remember. So that was the original experiment that I read, and I'm now working with people, researcher in psychology, so that we can push the experiment to be more complex based on what we can provide in terms of visualization, especially with mixed memory, where we put many data together, and I can provide a method of visualizing it. I can provide a computational process of retrieving it, but we need to understand from the human side how we retrieve the data, so I can improve my computational procedure more. So that conclude my presentation. We know that if we understand the human memory, how it works, it can help us a lot in engineering, in designing the computer that can perform much better than the computer we have now. But at the same time, the memory that we have in the computer can also permit us to take advantage even at this intermediate result point to help people in psychology to push for further understanding. So that's my basic work in computer science that I like to share with you. But I like to ask you a question. Can we do something with the new computer? And that's my conclusion. Thank you very much. And also, I'd like to thank the translator who did the translation into Spanish.